Okay. I'm going to start because I have some things to say. First, we were having a casual conversation about things like, I don't know, about other things beyond CS225 up here in the front informally. And it made me remember that I want to tell you my two biggest regrets from undergrad. Okay? So, you know, I don't do the, oh, when I was your age thing very often because, you know, I don't like to admit that that's a thing, but I do have two regrets from undergrad, just in case they strike a chord with you. One was that in my university there was the discrete math class, and there was the follow-on to the discrete math class that was a little bit different from our algorithms class here, and it was taught by Don Knuth, who, you know, is like this famous guy in computer science. And I didn't get it, and it was the last time he ever taught this class. It was called Concrete Math, the Concrete Math class. And I didn't get it, how important it was for me to like always go to class and to understand that I was in the presence of greatness and I should be sitting in the front row right here. And so that's one of my regrets from undergrad, because I didn't go every time. I didn't go often enough. But you're all here, so you don't identify with that at all, and I'm not great, and you're still here, so you're amazing. The other thing that I regret is not having studied abroad. And the reason I didn't study abroad is because I thought I couldn't afford it, right? Like it felt indulgent to do, but it was that I didn't understand at the time that, number one, there was a lot of support for doing it. There are a lot, and it's true of this university too, that there are a lot of scholarships and other support for studying abroad. And the biggest thing I didn't understand was that eventually in life, the $1,000 extra it would have cost or whatever is very little compared to the experience of the thing. So don't fail to study abroad just because you're in a hurry to get to your job. It will change your world and make you broader. So there you go. There's my little lecture for the day. Wade's rolling his eyes. Did you study abroad? Ah, see? Oh yeah, he says it, and you guys are like, oh, well then. Yeah. Fine. Okay, so let's see. Announcements. MP5 is out there and ready for you to contemplate. I've already seen some, so one of the reasons I love MP5 is because you can see bugs in it. Like if you do things incorrectly, oftentimes the image will get created incorrectly. And so there's this visual feedback for your debugging cycle, which I really love. I don't know if the posts on Piazza that I've seen have been public or not, but you'll probably see some at least throughout the course of MP5. You have to express some gratitude to the course assistants for this course, because at our last staff meeting, I said, the extra credit is due Friday. They can get that in. And course staff said, why are you doing that to them? Why not extend it? And of course staff always wins. So this will actually be due, no, not that day, this day, which is the Monday following spring break. So we'll give you a day after you get back to get it in. And that's all course staff, that's not me. I wanted to save you from that burden. So what they did to you here is they gave you the opportunity to ruin your spring break with it. Just kidding, no, just kidding. It's a good move. Okay, so any administrative questions or issues? Oh, I should also tell you that we're working on the grading. We're trying to get it done. The delay on the corrections to the quiz solutions, that's all me. It's in my stack of stuff to do. So, yeah, Neil? A date by which we'll give you feedback on the credits, the problems of the day? No, I have no idea. You're doing them, you're doing fine. Oh, you mean like solutions to them? Oh, you know, you're welcome to share your solutions to the problem of the day. It's not a big secret, right? Yeah, it's not like exams and MPs and stuff like that, where the problems of the day, you go, get your understanding, use them as a learning tool. So, all right, that didn't directly answer the question. Okay, so that link right there is to the application that I showed you last time for binary search trees. I guess I can play with it for a minute again. So remind me very quickly how you would test to see if this is a binary search tree. Yeah, you can do the eyeball check, which is kind of a quick left to right scan to make sure that for any node, all the keys to the left of that node are, just kidding, are less than that node, and all the keys to the right of the node are greater than the node. Is spring break here yet? I'm really sorry. All right. Or you can do an in-order traversal, throwing down the keys as you say them and making sure that every key that you output in your in-order traversal is bigger than the one before. If you get to the end and you have increased the whole way, then what you've got is an in-order traversal. I'm sorry, a binary search tree. Duh. Okay, let's see. So I want to remove key 55. I want to remove key 55, and I think I'm going to change. I think I can do this. Oh, I don't know how to do it. I want to remove key 55 because I don't like it. Uh-oh, I didn't bring my keyboard. What I want to know is what's going to happen if I do this. If I remove key 55, what's going to happen? Yeah? You have to say really loud. Very good. Okay, so if I want to remove 55, my tree falls apart. The subtree rooted at 55 falls apart. And so you need glue to glue it together. The glue that this algorithm, the glue that his algorithm chose would find the value in the tree directly before 55, which in this case is 41. Use 41 as the glue and basically cut 41 out of the tree, okay? Now, this algorithm will not do that. This one instead notices that you could either use the number directly before 55 or the number directly after 55 as the glue to keep your tree together. This one happens to choose the successor, the one that comes after it, and in this case, that is 81. That's right. So we're going to use 81 to glue the tree back together in this particular application. Okay, slow it down a little bit. Come on. Oh. All right, so we're going on a search for 55 because that's what we want to remove. Oh, look, found it. Now we're going on a search for the glue. And basically we're going to find the leftmost thing. Oh, and then we're going to grab the glue and pull it up. That's it. Any question about that? Yeah, Mark, what's up? Oh, okay, so his question is actually, what happens if you remove 92? What happens if you remove 92? Yeah? Yeah, very good. So then there is the observation that, look, you know, 92 is just, it only has one child, right? So it is already part of a sequence. Wait a minute. Well, let's see what happens, shall we? We'll see what happens. I'm not really sure how this one is implemented. remove 92. Ready? Okay, so it will find 92. It has one child, which means cut it out and pull up its child to its position. Okay, so remember that when something has one child, it treats it as if it's a node to be removed from a linked list. It's just that in this case, that node to be removed from the linked list is the first node, so it's not like in the middle of the list. Okay? All right, what else? Anything else you want to see here? Yeah? Remove 37. Okay, I don't know what's happening here. All right, so is 37 easy to remove? It's like cutting it out of a linked list, right? 37 is going to go away and 41 is going to come up. It's as if these three nodes, 35, 37, and 41, are like in a list, basically. Okay, so let's do it. Remove. I'm not good with this mouse. 30. Oh, wow. Go. Search for, looking for 37. Okay. It has one child, so it's going to just zap it out and pull up 37's child. Okay, any question about that? Tell me the easiest vertices to remove. Raise your hand with the number of super easy vertices to remove in this picture. Super easy. I think 3, right? Those leaves, snip off the leaves. All the leaves are super easy. Okay, that's all I got for removal. Do you want to talk about anything else about removal, or you have any questions? I'll give us another tree so you can ask your questions if you like. Oh, make me another one. Woo. You like this tree? Yeah, I don't like this tree very much either. In fact, I don't like the trees that this applet makes by default. They're always these long, scraggly things. So that means we better have a way of avoiding such nonsense. Yeah. So if we capture that feeling of not liking those long, scraggly trees, the essence of our discussion is essentially we like mountains instead of sticks. We're going to refer to the long, scraggly trees as containing sticks, and we're going to refer to this alternative configuration as a mountain. Okay, so when I'm talking about 3 nodes in a chain, I'll just say, oh, that's a stick. This is a mountain. Those are not technical definitions. And I'm a little worried about that little blue thing right there. How about you? Oh, gone. No problem. Okay, so we like these things. We don't like these things so much because they're tall, they're long. All right, last time we defined this measure on a tree called its height balance, and furthermore, we defined a tree to be height balanced if it's empty, so empty trees are height balanced. If a tree is not height balanced, if a tree is not empty, which we say by saying, oh, it has at least a root. Maybe TL and TR are empty, but it has at least a root. If T looks like this, and the height balance of the tree is, you want to say 0, right? You want to say it's balanced. It's perfectly balanced. But the problem is we can't make very interesting trees like that. We can only make perfect trees. So what we do is we demand that the balance be off by no more than 1. Okay, so we allow the height balance to be off by 1. Okay, and furthermore, TL and TR are height balanced. let's see, if t equals this, and yeah, all right. It's complete. Any question about that? Okay, so is this tree height balanced? Is the stick height balanced? No. The balance of the left subtree, I mean the height of the left subtree is -1, and the height of the right subtree is 1, right? See how that works? But you know what? You can eyeball it and go, oh, look, the difference is 2. It's always a difference, whether you count it as the empty tree or 2 minus 0. However you want to count it is fine. Okay. Furthermore, usually B here, usually that balance factor is an absolute value. Usually it's an absolute value, but technically the correct subtraction that we do is R minus L, okay? It doesn't really matter because we usually have this, but I'll correct it anyway, yeah? Because otherwise this would be a height balanced tree. Is that one a height balanced tree? You see what I'm talking about? This one. Is this one a height balanced tree? So the balance factor here is 0, right? And this is a height balanced tree and this is a height balanced tree. Okay, if I didn't include that last thing, then this would be considered a height balanced tree, right? If I didn't specify that these two things also have to be height balanced, then that tree right there would be a height balanced tree. And it is not. Do you see that it is not height balanced? Because here's a subtree that is not balanced. Okay? All right. So the other way to describe that constraint that TL and TR must also be height balanced is to say that the definition is true recursively. That is, it's true for all the nodes in the tree. Height balance at every node differs by no more than 1. The heights for every node differ by no more than 1. All right, any question about those definitions? Okay, so here's a tree. And what I want from you, first of all, is this tree balanced? Height balanced? No is correct. And what I want to know from you is the key lowest in the tree that is the root of a subtree that's out of balanced. Lowest in the tree, so of least height. Okay, so the root of the subtree of least height that is out of balance. So I admit the whole tree is out of balance because the height of the right is 3 and the height of the left is 1. 3 minus 1 is 2. Out of balance. But I want to know what is the root of the subtree of least height, or the subtree lowest in the tree, actually, that is out of balance. Do you see it? Yeah, 80, really good. So 80 is the root of a subtree that's out of balance right here, okay? And I'm gonna grab hold of that 80. Now, what I think you're observing, I could be wrong, but what I think you're observing here loosely is that these together look kind of like a stick, okay? So you've got this out of balance, and you've got this thing that looks kind of like a stick there. So here's what we're going to do. We're going to wave a magic wand. Well, it's really a piece of code, a piece of magic code over this tree, transform the structure of the tree without breaking its binary search tree property. Okay, and we're going to do that by simply turning that stick into a mountain. Okay, so it looks something like this. We're going to take the stick. I'm going to draw it a little piece at a time. We're going to take the stick and turn it into a mountain. So that means we kind of pull it up and bend it. Okay, so here's your mountain. I do like mountains. There's your mountain. Okay, that replaces the stick in the tree. Now we're going to observe that that stick had 1, 2, 3, 4 places where we can add subtrees, and the mountain also has 1, 2, 3, 4 places where we can add subtrees. So what we're going to do, we're going to take those subtrees as they appear on the stick and place them in the same order as they appear in the mountain. So here we might call this one, here's one, here's another one, here's another one, and here's the 4th one that just happens to be empty. And we're going to put them in the same order in the new tree. Okay, so that means I'm going to have a 60 here. I'm going to have an 85 here. I know this one goes this way, and the value is a 95. And then this one goes this way, but there's nothing to add because it's an empty tree over here. Okay? Any question about that? And now we're just going to build the rest of the tree as it appeared before. Okay, so the only thing that has changed is this subtree that I'm pointing to. The rest of the tree is going to be exactly the same as it was before. So 50 points to whatever this subtree is. We've got a 30, a 20, and a 40 hanging out here. Okay, so do you like what we just did? There are 2 things to look at. There are 2 things to look at. First of all, did we break the binary search treeedness of this structure? No, we didn't. We could prove it. We could prove it using arguments about the order of these subtrees and how they appear here versus here. Okay? So we didn't break the binary search treeedness. Tell me about heights. Tell me about the heights of these 2 things, yeah? Yeah, look at that. We reduced the height of this tree, which means that we reduce the overall running time, the overall worst case running time of any of the algorithms that navigate the height of the structure. Okay? So this is overall kind of something that we expect to help us out. All right. So what just happened here? This is called a left rotation. It's as if we grab that stick and kind of rotate it up and break it, bend it into the mountain. Okay, so we call this an operation on the tree a left rotation. Okay, and we're going to use this operation and operations like this to control the height of these trees as we build them. So that's kind of where we're going. All right, now it's probably deeply unsatisfying to you for this to be a magic wand that we wave over our trees, right? You should write the code to do this. We'll do it together, and I'll get you started. Okay, so here's what we're going to do. I'm going to refer to this pointer right here as X. Okay, and I'll pretend that I have the reference to that actual pointer in 50's right child. I actually have 50's right, okay? And I'm going to refer to it as X. I'm going to get you started by giving you a temporary variable, and we'll call it Y, and it points to X's right. So I'm going to say Y equal X's right. Okay, that's the setup. Now I want to make an observation. We have essentially picked up X's right? We grabbed it via Y. So it's available for reassignment, right? We picked up X's right, and so we can assign it. So let's do that. X's right needs to become what? In the new picture, what does 80's right look like? I'm sorry, X is right. What should X is right be? Yeah? I think it should be 85, right? X is, I'm asking about what should this one be? Oh, not 80. X is right. Should be, oh, y equal X is right. I've picked it up. X is right should be, oh my gosh. I think I did this wrong last hour. They're broken forever. X is right. It's this. What should be sitting here? But it isn't. I did this wrong. It's y that's broken. It's y that's broken. Look what it means for, I'm sorry, this is authentic failure on my part, okay? Look what I did. I actually set, in my picture, I set y to equal x, right? They were pointing to the same thing. So what I did in the picture was y equal x instead of y equal x is right, okay? This is what y should do. Y should be pointing here if it is x is right. Raise your hand if you saw it and you wanted to tell me that. Like you're yelling at me in your mind. Okay, sorry. Yell louder next time. Okay? Now I feel like we can do it because what I want this one to point to is 85 in my example, right? What currently points to 85 is y's left. So x is right should become y's left. Okay, so now I have done this pointer. Okay, now I've picked up y's left, and so I can reassign it. Y's left, which is now, you know, what 90's left will be. 90's left should be, x is correct. And now I've picked up x. So what should x be? I can reassign it. X is available for reassignment. So what should x be in the end? Say it louder. Y. X should be y. Right? Hurry. All right. X is y's right. So I'm holding on to 90. I can reassign 80's right child. I do that, what should it be? It should be 85. How do I refer to 85? By y's left. I've picked up y's left. I can reassign it. What should 90's left child be? It should be 80, right? In the new picture, it should be 80. The way I refer to that is x. I've picked up x. I need to reassign it. The value it should be is 90. My handle on 90 is y. There, you can watch that in double speed if you want. Okay, I do have questions about this. What's the running time of that? What's the running time of this thing? These 4 lines of code, each of which is an assignment statement. Big O of, yeah, the observation is that if I had 1,000,000 nodes in my tree, even if I had a gazillion nodes in my tree, this operation would take the same amount of time. It doesn't vary with the size of the tree. This is a constant time operation. Okay? Any question about it? Yes? Yeah. Okay, so I think what you're asking about, so he's like, how do you know? How do you know that this is where we want to do this in the tree? Is that effectively what you're asking? So I'm going to decouple the operations themselves from the diagnosis of how to deploy them. So what we're talking about right now is the operations themselves. That is, how can we change the tree? Later on, probably not today, but at the start of the next time I see you, we'll talk about how do we figure out when is a good time to do each of these operations, okay? So right now, we're going to focus just on the operations. They're not very expensive, but they do change heights, okay? And we'll talk about that a little bit more too. All right, so as you might already have guessed, left rotations have an analogy for right rotations, right? In fact, if you pick up your piece of paper and look at it from the back side, it's exactly the slide, and you switch all the words that say left to words that say right, and it's exactly the same slide that I would have made for right rotation, right? You're taking something that's sticky on this side and you're kind of rotating it up into a mountain from the left to the right. All right, so let's test and see whether or not that analogy is sufficient. Now, what I want to observe here is that at 70, and granted 70 might be part of some larger tree, but at 70, we have an imbalance, right? It's long on the left. So we suspect in our mind that a right rotation will fix it. So let's try out our newfound skills at changing sticks into mountains, but this time do it from as a right rotation instead of as a left rotation, okay? I'm going to do it too and kind of talk aloud. You can choose whether to try to do it on your own or just to sort of follow along. So I have a stick. I'm going to bend it into a mountain like this. 40, 70, 20 is my mountain. Okay, that's a little binary search tree itself. And then I'm going to attach all the things I need to it. My 4 spots. 1, 2, 3, 4. The first 2 are empty. This one looks like this. And the last one is empty. Okay. It is. It's 80. You're right. Good. Okay. So I think I think I have done a right rotation there. Did I do it right? You think? You think I did it right? Let's take a look. Let's take a look, right? The thing I'm worried about are my triangles. There's an empty one, there's an empty one, there's a not empty one, there's a not empty one. Empty, empty, 50 with 60 on the right, and 80. So those are the right triangles. Now the question is, so I did it right, okay? I did the right thing. Do you like it? It's still out of balance. Shoot. So yeah, this is still an ugly tree. So what characterizes this? We thought maybe a right rotation would fix it because it was long on the left side. What characterizes the difference between this one and the previous one, say? Yeah? Yeah. So this one is long in a different place, is what you're saying, basically. We were kind of looking at the case where it was long on the stick side, right? That on the left side of the place that's imbalanced, if the imbalance is caused by something on the left, then it would be fixed by a right rotation. But this one wasn't. It was fixed by, or it was caused by being long on this side. Oh, someday I will be able to do that. Someday I'll be able to go. You want to make it connect for me, and I can. That'd be cool. All right. So it's the fact that it was long here that made that plain old rotation not work. So here's what we're going to do. We don't have to learn anything new to do this. We're going to take our strange situation and turn it into one that we're comfortable with. And the way we're going to do that is as follows. The first thing we're going to do is a left rotation about 40. So the first thing is left about 40. And you know how to do that. We already did it. Okay, so 40, 50, 60 becomes 40, 50, 60. Make the mountain. And then reattach all the key pieces. I think all we've got to attach is that 20, yes? And then above, the parts that don't change are 70 and 80. Now what we've got is this stick here. Okay, so now we're going to do a right rotation about 70. And I'll do that like this. All right, so I'm going to take 40, 50, 70 and put it into a mountain. 40, 50, 70. It's in a mountain like this. Okay. And I'm going to attach all the pieces. So here's 1, 2, 3, 4. Those pieces look like 20, then nothing, then 60, then 80. Okay, any question about that? All right, so now look, all of a sudden, this tree of height 1, 2, 3 is now a tree of height 2. We have changed the height of the structure. Now, again, it's the operation I want you to see, not necessarily the diagnosis for the operation. I want you to have the intuition, but not, you know, the programmatic, the algorithmic ability to diagnose this yet. There was a question somewhere. I know it. Yes? Yeah, well, I'm going to throw that right back at you. What's the runtime for getting from there to there? It is constant because it's constant to get here, and then it's constant to get here. Okay? So it's 2 constants. Any question about it? All right. So this one is called it's still a right rotation because we're still taking something that's long on the left and moving it over to the right. So it's still a right rotation, but this one is a left-right rotation. So we do a left first, and then we do a right rotation. So this is a left-right rotation. Okay? Any question about it? Now, of course, you can look at this through the back of your page and change all the lefts to right and rights to left, and you've got a right-left rotation as well. Okay, the mirror image of this holds. Okay. Oh, come on. How often does this happen to us? Does it happen every day? I should reboot my machine between. Okay, so let's do a little bit of a summary, and then I'm going to move up and do a little bit of an overview. So here's the summary. Just as we've said, there are 4 kinds of rotations that we're going to be interested in using to change the structure of our tree. Right, left, left, right, and right, left. Okay, with the expected symmetries. I think I have these written in the wrong order because these are both right rotations and these 2 are both left rotations. Okay, they are local operations. The fact that they are local operations is what gets us the constantness of this. It doesn't matter where we do it, only these few little nodes are affected by what we do. They're constant time, and the binary search tree characteristic is maintained. That is, we don't mess up our tree's order in any way. The particular rotations that we've got and that we're going to use to maintain a balance of binary search trees has a particular name. They are called AVL trees. And that stands for Adelson, Velsky, Landis. And this work was done in 1962. And it's two people. It's two people. They're called AVL trees. We refer to them as AVL trees. Okay, so here's the deal. AVL trees are not the only kind of height balanced trees. You will definitely run into red-black trees also in your experience. You'll probably see some adaptations of AVL trees like left-leaning or right-leaning AVL trees or various modifications thereof. I chose AVL trees specifically to talk about in this class because I really feel like if I took a binary search tree and put you in a closet and said, come up with an algorithm to keep this tree always balanced, you would figure it out. This one feels, you would create this. This one feels like one that we could have come up with on our own if we really tried hard to do it. And what I like about that idea is that if you had been born, 50 years ago or so, it could have borne your name instead. Computer science has gotten a lot harder than it used to be. All right, so that's why we do this one. You will see other ones. We're not anywhere close to being finished with this content yet. We've just introduced the idea of rotating the trees, and you've seen the detail. But what we haven't talked about is how to maintain the height of the structure. That is, how we always know how tall the subtrees are, but it seems sort of important, so we're going to talk about that a little bit. And we haven't talked about detecting imbalances and, more importantly, diagnosing the rotation remedy. So detecting the imbalance and diagnosing the rotation remedy or fix. Okay? All right, so let's keep going with this then so we get to that point. All right, so here's a tree. Is it in balance? Is this tree balanced? Is it? No, okay. Tell me the lowest node in the tree that's out of balance. Or the subtree of least height, yeah. Okay, 5, good. Okay, so this one is out of balance. What kind of rotation fixes it, do you think? I know that we haven't diagnosed it, but what kind of rotation do you think would fix this? Some kind of right rotation, right? Because we want to kind of pick it up and shorten it on the left. So some kind of right rotation. Do you expect it to be a single right rotation or a double right rotation? So here's what you're going to do to judge, and we'll talk about this more later. You look at the node that's out of balance. You think it's going to be a right rotation, so you look at its left child and you determine whether it's this side or this side. If it's on the inside, it's going to be a double rotation. That is, if it's back toward here, it's going to be a double rotation. If it's out this way, it will be a single. I like to think of this as a dog leg instead of a stick. So we still have something that's stringy. It's just a bent string. Bent stick, an elbow, that. All right, but that's not what this one is. Okay, so here's what I want to know from you. I want to know if we do the right kind of rotation here, that's a single rotation, whose heights change. So just sketch very lightly over your page and show me the nodes whose heights change upon a rotation. Okay, just take a second, look at your tree, do a brief sketch, think about, if you were to do a rotation, which of the nodes have heights that change? Got it? You may need two hands for this, but I want to know the number of nodes whose heights change. So you want to show me? No way. None change. 2. Okay, so when I say height, I mean the height of the subtree rooted at a node. Does this one's height change? No, right? That's part, here's the stick. The part of the tree that doesn't change for sure is all of this, right? There's no way. We're not changing anything over there. So already, the heights of those the subtrees rooted in each of those nodes are not going to change. Remember, height is a distance from a node to a leaf. Distance from a node to a leaf. Those can't change because nothing changes about those subtrees. Does 6's height change? No. And in fact, if 6 were the root of a bigger tree, none of the heights would change. How about 4? Nothing in 4. 4's height can't change. Height looks down, right? The distance from the node to any leaf. It might have a new parent, but it will not have new children. 4's height doesn't change. How about 2? Nope, same story. It's just something we're going to carry around. How about 1? No. 1 happens not to change. Okay, all right, so look at this. If we do this rotation, the only vertices whose heights change are these, and ultimately, this one will too. We'll talk about how we get at that later. But look at this. I don't have to do a lot of traversing this tree in order to compute heights because not very many heights change. In fact, to update the height of 3, I only need to know the height of this tree and the height of this tree, right? I only need to know those heights. Well, guess what we're going to do? We are going to store inside every node its height. So in order to update the height of 3, all I have to do is look inside this node for its height, because I'm keeping it there. Look inside this node for its height, because I'm keeping it there. Take the max of those two values, add 1, and that's the new thing that I'm going to put inside the node corresponding to 3 in this picture. Okay, so now how do I update 5's height? How do I update 5's height? Anybody want to describe it? Yeah? It's going to be 3's height, 5's height. Well, oh, so we don't have to know. I see what you're doing. Upon the rotation, you're like being careful because you're, yeah, but it might not actually be that. It might still be constrained by 6. So, but that's okay. All we have to do for sure is look at 6's height, which we know. Look at 3's height, which we know. Take the maximum of those two and add 1. So 6 may still win, I think, or it will be a tie, maybe, depending on that criteria. But we don't have to think that hard. We can always look at the children, take the max value, add 1, and update its height. Now, this idea of storing heights inside nodes might kind of bother you at first. Like, oh my gosh, we never had to do that before. But here's the thing. You did keep the size of, well, it's a little bit different, I guess. But you kept the size of a list inside the list class, right? Here, We're just storing something inside the node class that tells you a characteristic of the node itself. We're going to keep the height inside the node for each one of these nodes. Okay, so that's a little bit of a change. All right, hold on just a second. I want to just say what's coming next. The very next thing we're going to do is identify when rotations are useful to us. So the very next thing is, how do we make this do what we want to a tree? Okay, bye. Yeah, of course.